Hi, nice to see you again. Today we will solve problem number 23 of our list of Matlab problems. And in this problem we have to compute an approximation to number pi from this expression. That is, we will approximate number pi by computing the square root of the product between this series and number 6. I would like to highlight that this expression includes an infinite number of terms, so we won't be able to compute it with the computer. And for that reason, in question A, they ask us to write a Matlab script called, in this particular case, approxPy1, that computes the sum of the first capital N terms using a for loop, and that evaluates the relative error of the obtained approximation to number pi. Finally, they also ask how many correct significant digits do we obtain when we use 200 terms in this series. Before writing the code corresponding to that question, I would like to remember that given an approximation x bar to an exact value x, we say that this approximation has q correct significant digits when the relative error of the approximation is smaller than 0.5 times 10 to the power of minus q. So, from this equation, we realize that if the relative error is known, we can compute the number of correct significant digits, q, just applying logarithms to both sides of the expression. Thus, we obtain that the correct significant digits, q, verifies this inequality. And that's the expression that we will use to compute the number of the significant digits. So, to start, let's go to Matlab and set our default folder, and in my case that will be on the desktop, and I will create a new folder called Exercise 23, and I will set it as my default folder. Okay, so let's now to answer question number A. I will create a new script. The first two sentences of this script will be clear and CLC. Clear to clear the workspace each time we run our code, and CLC to clear the command window each time we run the code. Then I will add a comment saying that this is the answer to question 23A. And the idea is that I will fix the number of terms in a variable called num terms, that in this case will be 200. I put semicolon at the end of the sentence. And what I will say, we have to compute a summation, so that I will initialize the value of the summation to 0. And then I will loop for I equals to 1 until the number of terms, and in each iteration I will update the value of sum according to the expression 1 over I squared. So that way we get the summation, so the final approximation to pi, I will call it pi approx, will be the square root of 6 times the value of the summation. Once we get this approximation, we will compute the relative error. We'll call that relative error as the absolute value of the ratio between the absolute error, that will be pi approx minus the exact value of pi, which is pi in Matlab, divided by pi. So I will delete this. Okay, and once we get the approximation to pi and the corresponding relative error, we can compute the number of correct significant digits q as the logarithm in base 10, log 10 of dot 5 minus the logarithm in base 10 of the relative error. Sorry. Okay, so and this will be a real number, and the number of significant digits must be an integer number that will be smaller to that expression. Therefore, we will add, before this expression, we will compute the floor of this difference. Okay, so q will be the integer just below this quantity. So now we just have to run the code. Once we run the code, we are asked for a name. So that will be approx pi 1. And here we get the result. I will increase the command window, and the approximation to pi using 200 terms in this series is 3.1368, and the relative error is 0.0015, and finally the number of significant digits is also 2. We now can play a little bit with our script, and for instance, if we increase the number of terms to 2000, okay, that we will get, the approximation will be 3.1411, the relative error will be 1.5110 to the power of minus 4, and the number of significant digits will be 3. Okay, so that's our first script. Now we can move to the second question, that is just modify our code and use the while loop instead of the for loop. So we move back to the Matlab environment, and we will create a new script. Let me first of all increase this window. We will create a new script, and we will start from this version. So I will copy all the sentence. I select them, Command C, Control C if you are in a Windows machine, and then I will copy them, Command V or Control V. Okay, the structure will be really similar in this case. We only have to change this sentence for and this and substitute it for the while sentence. The while sentence is quite similar, but the main difference is that we have to write between parentheses here a condition that must be satisfied each time we loop on the while structure. So in this particular case, the condition will be that we have to we have to loop while the number of terms is equal or smaller to 200. So what we can say is that we can initialize I equals to 1 and then set loop while I is smaller or equal to the number of terms, which is 200. So in this case, we will loop inside the while structure while I is smaller the number of terms, num terms, which is 200. Each time we go inside, we will update the value of sum, but now we also have to update the value of the counter I. So with I equals 1, we check that this condition is true. I is smaller than the number of terms, so we will update sum as sum, which is 0 plus 1 divided by 1 to the square. We will increase the value of I put a semicolon at the end of the sentence, and then we will move back to the condition. Now I is equal to 2, since it is smaller to the number of terms, you go inside the loop again, and so on and so on. Finally, once I is equal to 100, I 200 is smaller or equal to the number of terms, which is also 200, and we will compute the last contribution and update the value of I to 201, and then you will skip the loop because the condition will be false. Once you are outside of the while structure, you compute the approximation to pi, the relative error, and the number of significant digits. So that's our code. In fact, we only have to modify the loop. We have to set an initial value to I, and we have to increase both, or we have to update both the value of the sum and the value of the counter I. That's all. So let's try to run the code, and we will call that approx pi2. And once we run the code, we get the same result. With 200 terms, the approximation to pi is 3.1368. The relative error is 0.0015, and the number of significant digits is 2. Okay, so let's try to answer question number C. Now, instead of prescribing the number of terms of the series, what we want to do is to prescribe a given tolerance. So if the number of the digits is 3, that means that the relative error will be smaller than 0.5 to 10 to the power of minus 3. How many terms do we need to compute this approximation? Okay, so to answer that question, we can just modify a little bit our code, and instead of writing this condition, modifying it by a condition that includes the tolerance of our approximation. So to do this, we will create a new script. We will copy again the new version of our code. Again, Command C, Control C if you are in a Windows machine, and Command V or Control V if you are in a Windows machine again. And then what we have to do is instead of prescribing the number of terms, we will prescribe a relative error. So prescribed relative error, in our case that will be dot 5 for times 10 to the power of minus 3. Okay, then we will set the initial value to sum and initial value to I, and what we have to do is to modify this condition. Instead of using that, what we have to do is we want to loop while the relative error is bigger than the prescribed one. So the relative error should be bigger than the prescribed relative error. So the idea is, if the relative error is bigger than the prescribed relative error, what do we have to do? Well, we have to update the value of sum, we have to update the value of I, but also we have to compute the value of the approximation and the relative error of that approximation. So to that end, I will copy these two sentences and move it, Command X, Control X, and move them here. So now in each iteration of the while loop, I will update the value of sum. I will compute the approximation to pi from this value of sum. I will add at the end of the sentence a semicolon. And from the approximated value of pi, I will compute the relative error. Also, I will write here a semicolon at the end of the sentence. I don't want to have these results in the command window. And I will loop while this relative error is bigger than the prescribed relative error. Now, the only thing that we have to do is to ensure that we will go into the while structure at least one time. So to that end, I will set an initial value to the relative error. For instance, something that is bigger than the prescribed value. For example, 2 times the prescribed relative error. So what we have now, and I add the semicolon at the end, so what we have now is we define the prescribed relative error, then we set the initial values for sum and the counter I. I set an initial value for the relative error, which is 2 times the prescribed relative error, so it is bigger than it, and then I check if the relative error is bigger than the prescribed relative error. Since it is bigger, I compute the first term in the series, I compute the approximation from it, I compute the relative error, and update the value of I, and I check again if the relative error is bigger than the prescribed error. And I will do that until I get the exact value, or a value that approximates, according to the prescribed tolerance, the exact value of pi. So now we run the code. Now the name will be approx pi 3. And now what we get is that the value the value of the value of the significant digits is 3. Okay, so it's something that we already know because we have prescribed that value. What we can do in order to see what the code is doing is to print in each iteration three numbers. For instance, the number of the iteration, the value of the approximation, and the value of the relative error. To do that, we can use the sentence f print f, okay, that allows us to write with a given format, with a prescribed format, the value of several sentences, several variables. For instance, what we can do is we want to write the value of the iteration, I, the value of the approximation, pi approx, and the value of the relative error, rel error. And now, in this part, between single quotes, we have to write how we want to write these three numbers. For instance, in this particular case, what I will say is, I will write iteration two dots and then the value of the iteration, and I will write it with a format of 4 digits, just as an integer number, because I, the number of iteration, is an integer number. Then I will write approximation, and I will use 15 digits with 8 digits for the decimal part, and I will use an engineer notation for that number. And finally, I will write the relative error, and I will use the same format. So that means, since it is a real number, 15 digits with 8 digits to the decimal part, and I will use engineering notation. And what is important is that we have to add the \n, the new line format, in order to write each time in a different line. Note that now this sentence is too long, and what we can do is to split it into lines, just adding at the end, after the comma, 3 dots and return. So now we have one single sentence split in 2 lines. Okay, so now what we can do is just delete this part here. We don't want to use it, and from this from this version we can run the code again, and what we get is that for each time we pass through the while structure, the code writes in the command window a sentence which is iteration. This is part here. Now the number of the iteration with 4 decimal digits, then the value of the approximation, which is here, using 15 digits in the exponent engineering notation, and finally the relative error of the approximation. And note that just at the last iteration, the error is below 0.5 10 to the power of minus 3. The relative error of the approximation is 0.49 10 to the minus 3, or 499 10 to the power of minus 4. So this is how we can use the while structure and how we can modify the condition in the while structure in order to obtain an approximation to number pi that verifies a prescribed tolerance. What's the problem? The problem is that if the tolerance is too small, then we will need a large number of iterations, a large number of turns in the series to get that accuracy. For instance, if we move from 3 significant digits to 4 significant digits and we run again the code, what we get is that now we need 6080 terms in the series to get that accuracy. If we reduce to 5 significant digits, then we need a really large number of iterations, which is 60,794 turns in the series to get this 0.5 10 to the minus 5 accuracy. So in order to avoid this kind of large number of turns, at the last question, we are asked to modify the code in order that the number of terms do not exceed a given number of terms, which is called max terms. So to that end, what we will do is to create a new version of the code from the one we have developed. So again, I copy all the sentences and I passed them in the new version. And now I will do the same. I will use the same code, but now the only thing is that I have to add which is the max number of terms, and this is max terms. It's equal, in this particular case, for instance, 5,000. Okay. And now we have to modify this condition here. And the condition, and we have to loop while the error, the relative error, is bigger than the prescribed tolerance, and the number of terms is smaller than the prescribed max number of terms. So what we will do is we modify this expression, this condition, by first add, we will have to add another term if the relative error is bigger than the prescribed error, and the number of terms, which is I, is smaller than max terms. So that's all. That's all. You only have to modify this, and then we will ensure that we will get an approximation that that verifies this condition and is computed at maximum with this number of terms. Just try to run now the code. This is approx pi 4. Okay, and that's it. In this particular case, we realize that with 5,000 terms, which is the number we get here, we get an approximation equal to 3.1414 and so on, with a relative error which is 6 times 10 to the minus 5. So this approximation is computed with 5,000 terms, but do not verify the prescribed tolerance, because the prescribed tolerance was 0.5 10 to the power of minus 5. Now, for instance, if we increase the number of terms to 10,000, we realize that we still get an approximation to pi that do not verify the prescribed tolerance. Again, if we increase the number of terms, for instance, 30,000, now the tolerance still is above the approximation, and the relative error is above the prescribed tolerance. Again, we will increase now the number of terms to 70,000, and at the end we will get an approximation with the prescribed tolerance in 60,794 terms. Okay, so that's all. And as a summary, what we have learned in this session is how to use the for sentence, how to use the while sentence, how to adapt the logical condition in the while sentence to different purposes, and we have also learned how to use the fprintf sentence to print some results in the command window. Finally, the last thing that we have reviewed is how to split one single sentence in more than one line in a MATLAB script. So I hope that this will help you to learn how to use MATLAB to solve problems, and I hope to see you again in the next session. See you. Bye bye.